In this example, we are given that a small ball of mass m moving at a speed u strikes normally on the rod of mass capital M and length capital L placed on a smooth surface as shown, and we are required to find the value of capital M, for which after collision ball will come to rest, and it is also given that the coefficient of restitution in the collision is small e. Now in this situation, as we can say, the system is at rest initially, and the ball will collide to the system of this rod, and as no external force and torque are present, we can say that linear as well as angular momentum of system will remain conserved. In this situation, if the ball will finally come to rest, the rod will eventually move with the speed v, as well as due to the impulse imparted by the ball, it will start rotating at an angular speed omega. So very first thing is, in absence of external forces, we can write by linear momentum conservation, or we can write initial momentum of the system was mu, and after collision, as ball will come to rest, the final linear momentum of the rod we can write as mv only. That will be, say, our equation 1. This will give us the final velocity of rod, which is small mu by capital M. And by angular momentum conservation, we can write here the initial angular momentum of ball with respect to the center of rod is mu L by 4, as it is traveling at a normal separation L by 4 from the line passing through center. This is equals to the final angular momentum of the rod, because ball will come to rest, so its angular momentum will no longer exist. So for the rod, we can write its angular momentum to be I omega, which is ml square by 12 into omega. This is your equation 2, from where we can get the value of angular speed of rotation of rod after collision, which can be directly given as this will be, you can see, 3 mu by capital ML. Now we can write the equation for coefficient of restitution. As we know, for restitution we can write the separation velocity is E times the approach velocity. As initially the rod was at rest, the approach velocity before collision was taken as u, and after collision, as the rod is moving with the linear speed v, every point of rod will move with the speed v, as well as the rod is having some angular speed omega. So this point, which is located at a distance L by 4 from center, will be having a translational speed. Total will be v plus L by 4 omega. So in this situation, by coefficient of restitution, we can write E is equals to separation velocity by approach velocity. Here after collision, ball will be at rest, so net velocity of this point of rod will be the separation velocity, which is v plus L by 4 omega upon the approach velocity is u. So from here we'll get v plus L by 4 omega is equals to u. Now we can substitute the values of v and omega over here. This will give us mu by capital M plus L by 4 into 3 mu upon ml is equals to u. From here this u gets cancelled out, L gets cancelled out. So on solving, we can see here the relation we'll be getting is this 4m we can take as LCM. So this will be 7m is equals to 4em. So in this situation, from here we'll get capital M is equals to 7 by 4m by E. That will be the answer to this problem.